Good morning. We have finished the first part of the third unit, that is dynamic force analysis of a slider crank chain mechanism. And the second part in the unit 3 is flywheels. So here we'll discuss first what is a flywheel, what is the function of a flywheel, what is turning moment diagram, and what is the corresponding equations we need to solve the problems. Those things we'll discuss in today's class. We have in another chapter called governor, that is the fourth chapter. Okay, and there is a difference between a flywheel and governor that we will discuss when we discuss the fourth chapter. At this moment, I will first explain what is a flywheel, for what purpose we provide flywheel. If you don't provide flywheel, what will be the problem, okay, and the importance of the flywheel, that we will see. Then we will see turning moment diagram for three different cases. One is double acting steam engine, and another one is an IC engine, and another one that is a single cylinder IC engine, and another one is a multi-cylinder engine. So we will see those turning moment diagrams. Okay. So first let us see what is a flywheel and what is the objective of the flywheel and where we need flywheel. This flywheel part we will see. So basically the flywheel is intended to store the energy. Okay. Flywheel is a device. It stores the energy and it provides when you require the energy. Okay. And it also reserves when it have more energy. It is something like a bank account. Of course, your money only, you will put it in a bank. Okay, when you have excess money with you, you will deposit in the bank. From that money, your money only, when you require, you will withdraw the money. This is every person will do unless he will take a loan. Under normal circumstances, when you have an excess money, you put it in a deposit, and whenever you require, you take that money. Okay, similar way, here we have a device called flywheel, which stores the energy when it have the more energy, and which provides the energy that when it needs the energy. Okay. So let us take a practical case, a punching machine or a punching press, how this flywheel is going to work, or what is the requirement of this flywheel in a punching press. Okay, you can see a flywheel is used to control the variation of the speed during each cycle of an engine. Okay. And it acts as a reservoir of energy. That is what I said. It serves two purposes. Okay, first purpose is actually fulfilled by by performing the second one. So it reserves or it preserves the energy. Okay, and it maintains a constant speed. Okay, variation in the speed is controlled in each cycle of engine. So it controls cyclic fluctuations. In the other way, we can say flywheel. So flywheel take care about cyclic fluctuations. As I said, governor, I am not dealing in detail this part, just I am giving the hint. Governor will take care about load fluctuations. Load fluctuations, that is the basic difference between a flywheel and a governor. what we said, it takes care about cyclic fluctuations. That means every cycle there is some fluctuation. That fluctuation is going to be taken care by flywheel, isn't it? Then what about governor? Governor will take care about load fluctuations. I'm not going to discuss this at this moment, but it is load fluctuations. Let us see what is cyclic fluctuations. Okay, let me give a simple classical example like this. See, we have in general 3 seasons like winter, summer, rainy. Winter, summer, rainy. Okay, whether it is doing that way as on today, true or not, keep it away, but we have these 3 seasons. We have more amount of rains in rainy season. Literally there is no rain in summer, and very, very less in case of winter. So let us assume there is a lake or pond or something. In rainy season, okay, the water will be seepage, or it will be absorbed by that soil, okay, or it will be stored in that, okay. And whereas when there is no rain, like summer time, that water, isn't it, is going to be used for the purpose of the requirements. So this is every cycle it happens. Every cycle means every year. Every year, it is 2020 Corona year, or 2019 some other year, or 2021, we don't know what is going to happen. Whatever the year it may be, this is same. This is what a cycle is. So it is a cycle. 1 year is said to be one cycle. Where there is more rain, that time it is preserved. So okay, and where summers and other winter season where there is no rain, the same water is going to be used. This is what we call a cycle and cyclic fluctuation. Okay, and take an example of a flywheel which is used in a punching press. Let us take a simple example. I need to prepare a washer. This is a washer. Washer by means of a punching machine. By means of a punching machine. So I take a blank of this plain blank, and I keep it on a platform or on a table or on a die. Then by piercing a tool called punching tool, I remove a material from here. Then this is removed. Then I get my washer like this. For this, what is the action we need? We need to strike this workpiece material, a device called punch. You can see here. So this is a plate, this one, and here there is a punch which gives this hole. Okay, this is a die. As I said, this is the die. On the die, this plate is placed, and there is a punch, and the punch is going to hit and cut, shear this material. So how this is going to happen? Say here we have shown a mechanism like a slider crank chain mechanism. This is a crank, this is a connecting rod. In place of this piston, I have kept my punch. Okay, when it rotates, this connecting rod oscillates and the punch is moving down. So let us assume this crank is at this position. So when this is at this position, my connecting rod is like this and my die is here, my punch is here. Suppose at this position, my crank is here, my connecting rod is here, my punch is here. Then I am not striking my plate, okay, but I am driving this crank, and the crank is connected to a motor, a constant power delivered motor, which supplies a power with a constant quantity. So that time I don't require more power to my punch, because the punch is not doing any activity. It is not doing any activity. But as the time proceeds, like it comes and hits, at that moment it is subjected to certain load. Okay, it subjected to certain load. Compared to the previous load, it's subjected to more load. So I have to give more amount of energy to my punch. But my motor is supplying a constant energy. So the beginning, I don't require more energy. That is when it is not hitting the blank. Okay, and whereas when it is hitting the blank, it needs more energy. So the motor will not take care about it. Then who will take care about it? A device called flywheel. That means when the punch is not hitting the workpiece during that time, the energy which is available more is preserved in the flywheel, and when it is hitting this workpiece, when it requires more energy, it delivers that energy excess which was stored earlier in the flywheel. Okay, that is a simple example of the punching where flywheel provides the cyclic fluctuation requirements. Okay, so we'll go for this flywheel analysis part and the terminology part for it. So let us look at a term called maximum fluctuation of energy. Maximum fluctuation of energy. So the flywheel will have certain mass which is said to be m, okay, and it will have a certain radius of gyration, that is k. So we know that moment of inertia is I is equal to mk square. We know I is equal to mk square. Okay, so where m is the mass, k is the radius of gyration, mk square gives the mass moment of inertia of the flywheel. Then, as I said just now, there is at one instant it runs at a low speed, and at one instant it runs at a maximum speed. So I define the maximum and minimum speed like omega 1 and omega 2. Omega 1 is the speed maximum, omega 2 is the minimum speed. Then what is the kinetic energy of the flywheel at mean speed? I defined it as a capital E. So what is actually kinetic energy of the flywheel? Kinetic energy of the flywheel is half I omega square. So if you write like suffix 1 and 2, it is a maximum and minimum speed, and I have used omega term for just for a simply like angular speed. So if I write omega 1, then it will be maximum kinetic energy. If I write omega 2, it is a minimum kinetic energy. So capital E is the kinetic energy of the flywheel at mean speed. What is mean speed? We can write mean speed is equal to maximum speed minus mean plus. Mean speed is nothing but maximum speed plus minimum speed by 2 is the mean speed. So if I write capital E, which is nothing but half I omega square. Then I used another term small e, which is called maximum fluctuation of energy. As I said, the maximum speed is omega 1 and minimum speed is omega 2. Then maximum kinetic energy and minimum kinetic energies are half I omega 1 square and half I omega 2 square. Its difference is called maximum fluctuation of energy. That is, small e is maximum fluctuation of energy. That is half I omega 1 square minus half I omega 2 square. Then, okay, this term, this k is different from this. This is the radius of gyration. And this k is the coefficient of fluctuation of speed. Some others use this as CS also. CS, coefficient of fluctuation of speed, is also defined as CS. So this is the notation which I used as per the Ratan textbook, which we are prepared following the book. So what is coefficient of fluctuation of speed? It is nothing but the ratio of the difference of the angular speed by mean speed. The difference of angular speed, that is omega 1 minus omega 2, and the mean speed is omega 1 plus omega 2 by 2, which is omega. So let me write what is maximum fluctuation of energy, E. So E is equal to half I omega 1 square minus half I omega 2 square. So if you take the I common, okay, if you take half I common, then it will be half I omega 1 square minus omega 2 square. This is a square minus b square, okay. So you can write a minus b into a plus b, and this 2 is taken inside, then I write I, okay, this is I omega 1 plus omega 2 into omega 1 minus omega 2. So what we defined omega 1 plus omega 2 by 2, what we defined omega 1 plus omega 2 by 2, we defined omega 1 plus omega 2 by 2 as omega. So I replace this omega, then here omega 1 minus omega 2. So for my simplification purpose, I convert it multiplying by this with 1 omega and dividing with omega. So if you multiply and divide with the same value, it will not change the value of it. So I omega square into omega 1 minus omega 2 by omega. So what we defined omega 1 minus omega 2 by omega, here we defined it as a k, that is a coefficient of fluctuation of speed. So you can write small e is equal to I omega square into k, or we can rearrange k is equal to E by I omega square. So if you want, you can rearrange in the other form like this. This is small e, okay, I omega square I write 2 into half into I omega square. So what I said, I omega square, half I omega square, omega is the mean speed, then half I omega square will become kinetic energy of the flywheel at mean speed. So I replace it E by, okay, so this is 2, half I omega square is E. So we can also write this is k is equal to E by 2E. We can also write it like this, k is equal to E by 2E, which gives the relation between coefficient of fluctuation of speed and maximum fluctuation of energy and kinetic energy of flywheel at mean speed. Okay, then we will see the turning moment diagrams and what is turning moment. Okay, so we have already studied in the first part of the third unit a term called turning moment, which gives Ft into R. So that is So during one revolution of the crankshaft, the torque T is given by Ft into R. So we have already derived the value of Ft in terms of F and theta and N. This equation is already known to you. That is Ft is equal to F sin theta plus sin 2 theta by 2 n square minus sin square theta under root, where theta is the angle made by the crank with the line of stroke, where n is L by R, that is ratio of length of the connecting rod to the radius of the crank, and F is the piston effort. So this is piston effort. So you can see the turning moment is not a constant, it is a function of F, R, theta, N. But N is constant because once we select an engine, the N value is fixed because its length of connecting rod and radius of the crank is not varied. Then R, once you select that, R is constant. F, the piston effort. So that is like how you get piston effort, P1A1 minus P2A2 plus F B plus or minus FB. So that P1A1, P2A2, A1, A2 are fixed, P1, P2 are variables. Okay, and the inertia forces also varying. Similar here, the theta is a variable. So one thing we can say, the turning moment is a function of the crank angle, that is theta. Okay, so if you draw a diagram between T versus theta, that is a turning moment diagram, that is the torque versus theta. If you plot a diagram which gives a turning moment diagram, T, isn't it? So the turning moment diagram gives a relation like how the torque is varying with respect to time, T versus theta. So here we have not considered the inertia of the connecting rod. Generally it is neglected to draw the diagram of turning moment diagrams. If it is required, you can consider. Okay, but in our analysis we have neglected. Okay, let us see various turning moment diagrams. So this is one of the typical turning moment diagram for a single cylinder double acting steam engine. Single cylinder double acting steam engine. You are aware of it. So in a single cylinder double acting steam engine, it gives power both from IDC to ODC or ODC to IDC. So inner dead center to outer or outer to inner, because it is a double acting, both sides. You have in a steam engine a D-slide valve which operates entering the steam from one side and leaving the other side. It gives the power both the left to right and right to left stroke. So in that case, I have drawn a diagram associated with this turning moment diagram. So there are two loops are here, that is OGP and PKQ. So this is, as I said, moving from one end to other end, that is 0 to pi. So 0 to pi, that is this cycle, outward stroke, and the inward stroke is PKQ. Okay, so this is the turning moment. So the area under this turning moment diagram is nothing but proportional to the work done per revolution. The area under this. So what is this area like? The area under this area, the hatched area, which indicates work done per revolution, because 0 to 2 pi, one revolution, 0 to pi that is outward stroke, pi to 2 pi inward stroke. So the product of this turning moment, okay, and the angle turned, that gives the work done. The product of the turning moment T and the angle theta, that gives the work done. So here, what is this line EF? How we draw this line EF is like this is the area which is shaded. This area, if you assume such a way that instead of this irregular path, if it is assumed that the area can be converted with a constant torque, what is that corresponding constant torque? That is called mean torque. So what I mean to say, the area, what is the area? OGP and PKQ, this total sum of area, okay, by the angle how much it turns, that is 2 pi. So the mean torque is nothing but the area. So what is the area? So area of OGP plus PKQ. So that is OGP PKQ by 2 pi. So if you write this, you get some amount of turning moment, that is what? This OE. So that is the magnitude OE. So a constant magnitude of turning moment, if it is applied, what it gives, that is nothing but this. In this case, you can see from A to B, the angle A to B, so this flywheel have more energy, that is what it requires, more than that it possesses, and whereas at B to C it have less energy because it is shortage of energy, that is why here it is shown minus and this is plus, and here also it is plus and here it is shown minus. Okay, so then coming to a turning moment diagram of an IC engine. So this is an IC engine, you are aware of it. There are 4 strokes named as a suction, compression, expansion and exhaust. So in expansion stroke we get the power, and the remaining 3 strokes we say we consume power. Literally it is not exactly correct. Some part of suction also there will be power obtained, some part of the exhaust also some power is obtained. That you can see. This is, the diagram shows, this is bottom, this is a negative and this is positive. So you can see in the suction, so 0 to pi, then pi to 2 pi, 2 pi to 3 pi, 3 pi to 4 pi. That is a 4-stroke engine which completes 720 degrees of rotation to finish one cycle. So in the suction stroke, first part is a negative, the rest second part is positive. And whereas in the compression, complete negative, and whereas the expansion, complete positive, and in the exhaust, so first part is negative, rest part is positive. In sometimes we forget about these things and we simply write, isn't it? These are also like negative loops, but strictly speaking it should be like this. So in the similar way, like what we discussed in the previous case, here also we can define a mean resisting torque. That means the total area divided by this 4 pi, which gives an amount called T mean. Like in the previous case, what I did, the area, I have shown 2 triangles area which I divided by 2 pi, whereas here this is the positive area and one more positive area and one more 3 positive areas and 3 negative areas. 1, 2, 3 negative areas, and this is 1 and this is 2 and this is 3. These positive 3 areas and these negative 3 areas summation by 4 pi gives a constant torque, that is a mean torque, that is T mean. And finally, this is a turning moment diagram for a multi-cylinder engine. This is the turning moment diagram for multi-cylinder engine. So what is this? Let us see. Instead of one cylinder, if you have more number of cylinders, simultaneously you have power strokes in one engine, another engine, another engine. As you are more number of cylinders, then your turning moment variation is a uniform variation. Here you can see there is a multi-cylinder engine turning moment diagram is drawn, where the turning moment diagram varies like this waveform. And similar in the previous case, here also if you draw a mean line, the mean line is the AO line. AO line is the mean line. So the energy which you can show here, the turning moment 1 is OA is a constant 1. Then here it is negative, and this is positive, this is negative, positive, negative, positive, okay, like negative. So the areas of all these like A1, okay, plus A2 is minus, then A3, A4, then A5, minus A6 is 0. So there is a mean energy, that is E if I write. So energy at each point at A is equal to E, and whereas at this point, like 1 by 1 if I write, so adding E plus A1, E plus A1 minus A2, E plus A1 minus A2 plus A3, like this, all these areas will become 0. The sum of the areas of above and below the mean line are 0. Okay, so let us have the last two definitions and we will finish the thing. What is it? One is maximum fluctuation of energy. How we define this? The difference between maximum kinetic energy and minimum kinetic energy, the difference is called maximum fluctuation of energy. When it will have maximum, when it will have minimum. So we have seen in the earlier slide that difference is maximum fluctuation of energy. And another one is coefficient of fluctuation of energy. It is nothing but the ratio of maximum fluctuation of energy to the work done per cycle. Okay, so in the next lecture we will solve the problems based upon the theory what we have discussed. Okay, thank you.